All right, I see a couple more people have tuned on. I just want to give it another minute or two here so people can find the stream, and then we'll get started here with Jeff. All right, I'll go ahead and kick things off now. My name's Cameron Breen. I am the Education Youth Programs Manager for Friends of the Dillon Ranger District. I want to thank everyone for tuning in here today. We've got a pretty awesome presentation. Jeff Simley was on the team that kind of created the maps on computers of all the streams and lakes in the United States for the U.S. Geologic Survey. I'm a big map guy. I really enjoy looking at them. So this is one I've been looking forward to. I met with Jeff early this year before we all got shut down into quarantine, and he kind of walked me through this presentation, and we're in for a good one. So it's something to be excited about. But also I want to thank Jeff for putting the time and effort into making this presentation for us. And he reached out to me at the beginning of the year and said he had something awesome to offer. So that's I'm really excited about it, and I'll hand it over to Jeff.
Okay, so I'll share my screen here, and let's see. There we go. So you should be able to see the a map of the terrain there. It's just a shaded map display of terrain, and this is in north central Colorado. And one of the things that makes the terrain here very interesting is the presence of this river, the Colorado River. And this river flows from Rocky Mountain National Park down through Kremling and off to Los Angeles. A lot of people think that the river flows to the Pacific Ocean, but it actually flows to Los Angeles because the water is rerouted to supply Los Angeles with drinking water, and also to a lesser extent, Phoenix and the Imperial Valley of California. So one of the things that's interesting about this spot here is that this river flows into it. This is the Blue River. The Colorado River is what we know as a level 1 river, meaning that it flows directly into the ocean. So anything that flows directly into the ocean is a level 1 river. So here we have a level 1 river. Then anything that flows into a level 1 river is called a level 2 river. So this river that we have at this junction here is a level 2 river. And this is the Blue River that flows into the Colorado at Kremling. And we have traced it all the way upstream to its headwaters near Hoosier Pass. And one of the things we can do is to take a look at this river and look at the drainage area around the river. That is everything that flows into this river, the Blue River. And so here we have that drainage area. So if you go up from the river and look around the ridge line, all along the river, it goes up to this black line that you see there, this black polygon. And this is what we call a watershed, or a drainage area, or a basin for the Blue River. And to give you an example of another basin, this is the Mississippi River Basin in the United States. So what you see there in blue is everything that drains into the Mississippi River that flows through New Orleans or that area. So that's a good example of a watershed or a basin. We can take a look at this basin and see there are some surrounding basins that are associated with it. This purple line that you see here is the Continental Divide, and it divides up basically the Atlantic watershed from the Pacific watershed. And the Blue River is in the Pacific watershed. Also, it divides up down here towards the bottom into the Arkansas River and over here into the Missouri River watershed, which is what the Platte River flows into. So just naming some of these, surrounding the Blue River watershed is the Colorado Headwaters watershed. And then over to the west is the Eagle River. Down to the southwest is the Roaring Fork. The Arkansas Headwaters over by Leadville are to the south, and then also the South Platte Headwaters. And then the upper South Platte River and Clear Creek. So those are the watersheds that surround the Blue River watershed. And here's a map of the major watersheds in the United States. We've numbered these to make them easier to reference. And you can see here that we're located in watershed number 14. And so this is called the Upper Colorado River. And then that flows into the Lower Colorado River, number 15. What's interesting also is that the Missouri River, 10, and the Arkansas River, 11, all of these watersheds, these three, 14, 10, and 11, the Upper Colorado, the Missouri, and the Arkansas, all intersect here at this one point. And that point is Mount McNamee, which is above the Climax Mine and is in the Dillon Ranger District. And I had the opportunity to climb Mount McNamee and pour water simultaneously into the Colorado, Missouri, and Arkansas rivers all at the same time. Here's a map of the United States where we subdivide these watersheds into smaller watersheds. And we're located in this watershed here, which is called the Colorado Headwaters watershed. And we can further subdivide that into smaller watersheds, which are right here. We're located in the Colorado Headwaters and then in the Blue River watershed. So these watersheds are kind of like zip codes. They allow water managers to divide the United States up into water management districts and kind of work as zip codes so we know where we are in the country. We take this larger Upper Colorado Headwaters, we can subdivide that down into the Upper Colorado Headwaters and then the Blue River Basin, which we have right here. So this is a way of how we subdivide up the watersheds. Interestingly, this idea of watersheds goes way back to the 1870s. And in 1890, John Wesley Powell looked at the watersheds of the Western United States, and he made this map, which was published in 1892. And this shows, color-coded the watersheds of the Western United States. And John Wesley Powell tried very hard to make these watersheds become the states. So instead of the rectangular shaped states we have now in the West, he wanted that the states to be shaped in the shape of the watersheds, because he realized that the big issue in the Western United States would be water management. And it was best if each water management area was also a state so they could better govern themselves. But John Wesley Powell ran into a lot of opposition in Congress. They didn't want the Western states to be shaped by the watersheds, but rather by the public land survey system, which gives us the square-shaped or rectangular-shaped states we have, such as Colorado is today. So here we are once again in our Blue River watershed. And we have an outflow point. This is down by Kremling, where the water flows out of the watershed. And then surrounding the watershed are headwaters. So no water flows into the Blue River watershed. All the water originates here and then flows at a single outflow point. So this is what we call a headwaters watershed. And we can subdivide the watershed into smaller watersheds. And we've done that here. This is what we call the HU10 divisions. It's kind of like taking a zip code and dividing up the zip code into smaller zip codes, like the zip code +4 thing that we have in the United States. Here we have the lower Blue River, the middle Blue River, the upper Blue, and then the Snake River, the 10-Mile River, and the Dillon watershed. So this is how we subdivide up the Blue River into water management areas. And here's an example of those water management areas with the hydrography superimposed on top of it. And each one of these multicolored polygons is a water management area that we just call a watershed. We can further subdivide the watershed up into even smaller units. This is what we call the HU12 level. And I'll just go through the sub-watersheds here. You'll begin to recognize some of the names. There's a Beaver Creek Blue at the very bottom or top of the picture, but at the bottom of the watershed. The Deep Creek Blue, the Elliott Creek, the Green Mountain Reservoir, the Slate Creek Blue, the Rock Creek Blue, the Straight Creek blue, and then the Dillon Reservoir watershed, the lower 10 mile, the Gold Hill blue, the west 10 mile, the upper 10 mile, the headwaters of the blue, the French Gulch blue, Swan River, Keystone Gulch Snake River, Peru Creek Snake River, the North Fork of the Snake, and finally the middle 10 Mile Creek watershed. So these are the names of the HU12 watersheds that we have for the Blue River watershed, which is also the Dillon Ranger District. So here's a way of displaying this on a map and looking at those individual watersheds. We can also subdivide this up into what we call catchments. And these are the drainage areas for each individual stream in the Blue River drainage. And we use this to calculate drainage area because drainage area is very important for calculating stream flow. How much water will flow into the rivers is largely governed by drainage area and precipitation. There are some other factors involved too, such as temperature and elevation, soil permeability, and things like that. But overall, the major issue here is drainage area and precipitation. That will pretty much tell you how much water will be in each individual stream. So here's the drainage area, the Blue River superimposed on a general map, just to give you some orientation of where things are. And we're going to look now at some of the notable streams of the Blue River. So this is a map of the major streams that are in the Blue River drainage. I'm just going to name these as we go through here. First of all, the Blue River, of course, is the main drainage for the watershed. Then we have some tributaries, such as the Snake River up towards Montezuma and Keystone, and 10 Mile Creek. And down at the farther end of the drainage area is Spring Creek, and then an Elliott Creek, and another Elliott Creek, and Cataract Creek. A lot of you have probably gone hiking up in the Cataract Creek area. And then Black Creek, Brush Creek, Slate Creek, Boulder Creek, North Rock Creek, South Rock Creek, and then the North, Middle, and South Willow Creeks, Meadow Creek. One of my favorite hikes in the Dillon Ranger District is up Meadow Creek, and North 10 Mile Creek, another popular spot over by Frisco for hiking. And then West 10 Mile Creek, which goes up to Vail Pass, past Copper Mountain, and goes to Vail Pass. And then Miners Creek, the Swan River, Soda Creek, which is familiar to people over by Keystone, know about Soda Creek. And then Deer Creek up towards the Continental Divide, and Peru Creek up into the Argentine Basin, and Straight Creek, which I-70 follows up to the Eisenhower Tunnel, and finally Acorn Creek, another nice hike in the Dillon Ranger District. So these are the major tributaries to the Blue River in the Dillon Ranger District. So once again, here we have the Blue River. And we have something that we call artificial paths. And these are segments of the river system that are wider than 50 feet. So the Blue River, most of the way down from Dillon Reservoir, is more than 50 feet wide. So we count that as what we call an artificial path. And I'll talk more about that in a few minutes about what an artificial path is. And then all these little dots you see there, those are lakes that are larger than 100 feet across and marshes that are greater than 100 feet across. Those are all mapped, and they have what we call artificial paths inside of them. The next thing we want to do is to show the streams of the Dillon Ranger District that are perennial, and that means that they flow all year long. So this is an example of a perennial stream. You can just tell that it's going to flow all the time because it's nice and wide, has a lot of water flowing through it. And these are the perennial streams. So here's a map of the perennial streams of the Dillon Ranger District, in addition to the artificial paths. And then on top of the perennial streams, we also want to add in what we call intermittent streams. And this is an example of an intermittent stream. It flows only during snow melt or a heavy thunderstorm. And so right now the snow is melting, this river has water in it, But later in August and September, it'll dry up and won't have any water in it. That's what we call an intermittent stream. So here's an example of the intermittent streams plus the perennial streams plus the artificial paths in the Dillon Ranger District. Another type of river that we have is called an ephemeral stream. And this only has water in it after a thunderstorm or major snowmelt. Here's another example of an ephemeral stream. So as you go hiking, you'll see lots of these across the landscape. They don't have any water in them, but when it rains with a heavy thunderstorm, then water will start to flow through this, and we call these ephemeral streams. And here's an example of the ephemeral streams in Summit County in the Dillon Ranger District. So the ephemeral, intermittent, perennial, and artificial paths, and then also canals. We have a few canals or ditches in the Dillon Ranger District, and this is a map of all that hydrography. So what I've done here is color code these things. So the canals are orange, the ephemeral streams are brown, the intermittent streams are light blue, the perennial streams are dark blue, and the artificial paths, that is the streams that are more than 50 feet wide or in lakes, are purple. So once again, here's the artificial paths in purple. Here are the perennial streams in dark blue, the intermittent streams in light blue, the ephemeral streams in brown, and the ditches and canals in orange. And most of the ditches and canals in the higher end of the Dillon Ranger District were built originally during the mining times for diverting water for hydraulic mining. And so we have a number of streams there. In the lower part of the Dillon Ranger District, most of the ditches and canals are for irrigating hayfields for livestock. So here we've composited all this together, and this gives us a picture of the streams of the Dillon Ranger District, color-coded by the type of flow that they have, whether they be perennial, intermittent, or ephemeral. So one of the things we do with these streams is we want to know which way they flow. So here we just have a mass of streams. It's kind of hard to tell which way they flow, but the computer has coded into it the flow direction. So these arrows will show us that flow direction that's encoded into the computer model of the data. That's very useful then for navigating upstream and downstream and finding out where the water goes and where it came from. So here's an example of Green Mountain Reservoir. This is what it looks like, all the streams, whether they be intermittent or ephemeral, flowing into Green Mountain Reservoir. But we need to be able to route the water through the reservoir. And by this map, we can't do that. So we add in these artificial paths that you see here, and that allows us to connect the dots essentially and get water to flow all the way through the system, through these lines, these purple lines. And then the lakes that we have in Summit County are two major reservoirs. There's Green Mountain Reservoir, located right down here, which was built by the Bureau of Reclamation back in 1938. They started building that. And then Dillon Reservoir, which was built in the 1960s. They actually started building the dam in 1961, finished it in 1963, and the lake began to fill up. The idea for Dillon Reservoir started way back in the 1900s, and early on in the 1900s, they decided that they could dam up that area there and divert water towards Denver. And in 1940, they actually started building a tunnel between Lake Dillon and Bailey, Colorado, a 23-mile long tunnel called the Roberts Tunnel, to divert water from the Dillon Ranger District towards Denver. Then we have Marsh, and you can't see very much here. That's because there just basically isn't very much marsh, but there is some out there. Then there's also reservoirs. Now, we call Lake Dillon and Green Mountain Reservoir reservoirs, but to the scientists, they're really called lakes. And a reservoir is something that is a man-made structure for impounding something. And a good example of that is a Climax mine. You've seen the mine tailings up there, and those are what are classified as being reservoirs. And then there's ice. Ice is also another part of the hydrography, and in the Gore Range, we have some areas that are made up of permanent snowfields, or what we call ice. So if we composite that together, we have the lakes and marshes, reservoirs and ice. Then we can add on top of that the perennial streams, intermittent, ephemeral, and canals and artificial paths. And this gives us a fairly comprehensive picture of all the water in the Dillon Ranger District. We can also add in the perimeter, which is that zip code kind of thing that I talked about, known as the HU8 boundary or the watershed boundary. And then we can subdivide that into the smaller boundaries. And this is pretty much what the water structure looks like in the Dillon Ranger District. So we're just going to zoom into a few areas here. Here we've zoomed into Dillon Reservoir, also called Lake Dillon. The official name is Dillon Reservoir. It's also known as Lake Dillon. And we can see the artificial paths going through the lake to route the water through. These artificial paths are actually the original streams. This is the Blue River. Here's the Snake. Here's 10 Mile Creek flowing through the bottom of the lake. And then we can see these other hydrologic units for managing the water. This is the Dillon unit. Over here is the lower 10 Mile unit. And going up the lower 10 Mile unit is the north branch of 10 Mile Creek, North 10 Mile Creek, which goes up quite a ways to the Gore Range Trail. In the Dillon watershed, we have Meadow Creek, which goes up towards Buffalo Eccles Pass. That you can hike, a nice hike up there. And so that's this area. Here's another area. Here's Peru Creek and the Snake, the North Fork of the Snake, Keystone Gulch. And I've color-coded these here so you can see the darker blue lines, which are the perennial streams, the brown lines, which are the ephemeral streams. Here's a case of a marsh here. Here's another area in the Gore Range. Example of a perennial stream, an intermittent stream, an ephemeral stream. Over here we can see Boulder Creek, and here's Boulder Lake. And you can hike over to Boulder Lake. That's a really nice hike. You get there by going up North Rock Creek, driving up and then hiking, and then getting on the Gore Range Trail and taking that over to Boulder Lake. We have an example of a marsh here, of a lake, of ice, and the basin boundary. And here's another area over by Climax. And here we have those reservoirs, those Climax tailing ponds. There's an example of a ditch there, and Clinton Gulch Dam Reservoir we've also shown. And here's the Upper Blue River hydrography. And you can see the detail of the streams there. One of the things we can do is we can subdivide this up into the individual catchments, which are the drainage areas for the individual segments of streams. And once again, that's very useful to hydrologists to understand how much drainage area there is in a particular area. So here's a picture of those drainage areas just by themselves. And they look kind of square, rectangular. They have a lot of 45-degree angles in them. The reason for that is because the underlying digital database of the elevation data is in a matrix or a square. So when the computer determines drainage areas, it kind of does so in this kind of rough pattern of these lines like this. So that's why it looks a little odd, but it's very close to the actual drainage areas, so close that there's no point in making it a finer drainage area design. Another thing that we have in the water of the Dillon Ranger District is what we call events. And these are things that help us monitor and understand how the water works. So here are those events that are in the database. And we have things like a basin outlet is an event. A dam is an event. It affects how the water flows. And we have something here that we call an active stream gauge in a water quality monitoring station. So the U.S. Geological Survey actively monitors the flow of the water and also the water quality by regularly sampling the water and determining its constituent minerals and things like that. There's an inactive stream gauge. There are a lot of stream gauges that were sampled at one time and are no longer sampled, but we call those inactive stream gauges. and then there's an example of a diversion outlet. So these are some of the events that are linked to the data. Here's an example of a stream gauge. This is the Colorado River stream gauge down by Kremling. And basically the y-axis here tells us how much water is flowing through in cubic feet per second. So hydrologists measure water by cubic feet per second, which is what we call flow volume. And here at this line here, you can see there's 1,000 cubic feet per second. It goes up to 10,000 cubic feet per second. And that happens sometimes in July when there's big spring melt off. Sometimes you see gaps in the water. That's in January when the river is frozen and we really can't measure the stream flow. So that's an example of what we call a hydrograph that allows scientists to understand the flow of water through a particular point. So here's a zoom in of Lake Dillon once again. We have a couple of dams in the database, some stream gauges, a water quality station. Here's an inactive gauge. That gauge was operational before Lake Dillon was built, and at one time was measuring the water flowing through the lake. Another way of looking at the water of the Dillon Ranger District is to look at what we call stream order. And basically stream order is a way of organizing the streams by how they are arranged in the network. So all the red lines you see there are what we call first order streams. They're the headwaters. There's where the rivers originate. And I'll zoom in here so you can see this a little bit better. All those red lines are what we call headwater streams. And they are the origination of the stream network. So we call these order 1. And then where order 1 streams join together, we call those order 2 streams. And then where order 2 streams join together, we call those order 3 streams. And it goes on down through the network. So we have order 4 and order 5 and all the way down to order 6. So what happens is that as you go down the stream network and you go up in order, the water is going to have more and more, the streams are going to have more and more water in them because they are the accumulation of lower order streams upstream. So the order 1s flow into the 2s, into the 3s, the 4th, the 5, the 6, and so they'll naturally have more water in them as you go through the order of streams. So here's an example of taking those order of streams and then making the line weight equivalent to the stream order. So now we get a sense of where the water is in the Dillon Ranger District. And so the thicker lines have more water, the thinner lines have less water. And in this map here, I've exaggerated that a little bit to give us a better understanding of where the water is. So the usefulness of that is that we can take this basic map of all the streams that are in the Dillon Ranger District, and by looking at the order, we can make a map like this, which tells us where the water really is. Where are the streams that have a little bit of water, and where are the ones that have a lot of water. So let's just look at a composite of this. This is the order 7. So this is the lower part of the Blue River. It's an order 7 stream. These are the order 6 streams, just a few of those. These are the order 5 streams, the order 4 streams, and the order 3 streams, the order 2 streams, and finally the order 1 streams. So that's how we composited all this together to make a map of where the water is in the Dillon Ranger District. One of the things we can do then is take these drainage areas, and we know how much drainage area there is for a particular stream. We can then calculate the cubic feet per second that is flowing through the streams, either on a monthly or annual basis. So what we've done here is we've created a model of the Dillon Ranger District, and we've created 5 classes of water and made a map similar to the stream order map, but this map is a little bit different because it's actually based on drainage area rather than stream order. So in this map here, I've made 10 different classes of water flow. And in this one here, I've increased the maximum water flows a little bit here to make it look more dramatic and give us a better understanding as to where the water is in the Dillon Ranger District. And here I've enhanced it a little bit more. And here a little bit more. and each time trying to make it look like a better and better map showing us where the water is. And so we'll look at some of the rivers. As you look at this map, you can see that there are some major branches. And we're going to go through and name these once again, and so we have an understanding of as to what's what. So there's Spring Creek, and there's Elliott Creek. There's the other Elliott Creek. There's Cataract Creek, and Black Creek, Brush Creek, Slate Creek, Boulder Creek, North Rock Creek, South Rock Creek, and then the North, Middle, and South Willow Creeks, Meadow Creek, North 10 Mile Creek, West 10 Mile Creek, the actual 10 Mile Creek, and then Miners Creek, the Blue River, and the Blue River as it flows down through the watershed, and then the Swan River, Soda Creek, Deer Creek, the Snake River, Peru Creek, North Fork of the Snake River, which goes up over Loveland Pass, past Keystone and Arapahoe ski area, and then Straight Creek, where I-70 runs up, and finally Acorn Creek. So this is a model then of where the water is in the Dillon Ranger District and the names of all those streams. So in this map here, we're going to look at how much water is flowing through the rivers. And so in this particular blue segment is where the water is flowing more than 350 cubic feet per second. And on top of that, we'll add in a segment of where the water is flowing more than 175 cubic feet per second. And then in this display here, where the water is flowing more than 80 cubic feet per second, and then more than 40 cubic feet per second, more than 25 cubic feet per second, more than 12 cubic feet per second, and then more than 4.5 cubic feet per second. And this display here shows us, once again, those major tributaries to the Blue River, or the major streams in the Dillon Ranger District. And then more than 2 cubic feet per second. And in this map here, we'll just name these once again. So this is everything that has more than 2 cubic feet per second in it, and then the names of those streams. And then this is everything that has more than 1/2 of a cubic feet per second. And then this is a map of everything that has more than, anything that's classified as a stream over 0 cubic feet per second that we classify as a stream. So this is a map then of the classes of water in the Dillon Ranger District by cubic feet per second on an annual basis. So when we say that it has more than 0.5 cubic feet per second, that's averaged out over a whole year. During spring runoff, it might have 2, 4, 12, 25 cubic feet per second, but during the average of the year, it might have just 0.5. So let's look at some samples here. At the upper Blue River, where the Blue River flows into Lake Dillon, it flows annually at about 100 cubic feet per second. And then where it flows into Green Mountain Reservoir, it flows at about 382 cubic feet per second on an annual basis. And finally, where the Blue River flows into the Colorado River near Kremling, throughout the year, it averages 478 cubic feet per second. So here's looking at a few more rivers. The Snake River, where it flows into Lake Dillon, flows at 78 cubic feet per second. And 10 Mile Creek, where it flows into Lake Dillon, flows at 107 cubic feet per second. So let's look at some other spot checks here. Cataract Creek, where it flows into the blue, is at 23 cubic feet per second. Black Creek flows at 24, and Slate Creek flows at 28 cubic feet per second, where it flows into the blue. A few more. Boulder Creek flows in at 17 cubic feet per second. North Rock Creek at 9. South Rock Creek at 8. And then North 10 Mile Creek, where it flows into 10 Mile Creek, just outside of Frisco, flows on an annual basis at 14 cubic feet per second. The West 10 Mile Creek at Copper Mountain flows at 27 cubic feet per second. And the upper 10 Mile Creek, where it joins West 10 Mile Creek, flows at 35 cubic feet per second. Swan River flows at 31 cubic feet per second. Peru Creek, throughout the year, flows at an average of 20 cubic feet per second. And then the Snake River flows at 20 cubic feet per second. And then the North Fork of the Snake, which goes up over Loveland Pass, flows at 19 cubic feet per second. Straight Creek flows at 15, and Acorn Creek at just 3 cubic feet per second. So this is an example of how much water measured by flow volume in cubic feet per second is flowing in the Dillon Ranger District for the average of the year. So that's the end of that presentation. The next thing I'm going to do is to show you a GIS, and this is a piece of software that we can use to actually analyze the flow of water for an area. And this line here I wanted to point out, this straight line, is the Roberts Tunnel that diverts water out of the Dillon Ranger District. Here is Lake Dillon itself. Let's just take a hypothetical example of looking at, well, say a truck driving over Fremont Pass, and say that it overturns and a tank load of gasoline flows into North 10 Mile Creek. We want to trace the water. So what we'll do here is we'll zoom into a spot. And we'll say that the tanker truck overturned right here. We're going to put a
Hey, Jeff,
marker. Yeah.
I think you got to switch the screens over to the GIS one. It's still on the PowerPoint one.
Oh, okay. So let's see here. And let's see. There we go. Now you should see it.
We're on there. Perfect. Thanks.
Good, good. Thanks for pointing that out. Yeah, forgot to do that. Yeah, so we're just left off here. We had this scenario. We're going to trace the water downstream. So what we've done is we placed a green dot down here by the Climax mine, where the highway goes by, and we're concerned about a toxic waste spill in the water. So what we're going to do then is we're going to trace it downstream, and I'll just click this here, and this line here, this cyan colored line shows us then the pathway of the toxin downstream. Notice that it goes down the North 10 Mile Creek into Lake Dillon, flows down the Blue River, but it also flows out through the Roberts Tunnel towards Denver. So that's a concern. If we were to look further downstream where it goes, here we go, just zoom that in a little bit closer here. You can see where it flows down towards Grand Junction. Takes for a second for the lines to redraw, but it's kind of a little hard to see here. I could actually make it a red line to make it easier to see. Let me do that real quick. There we go. There's a red line, easier to see, and you can see where the toxin would flow on downstream. And notice when it gets down towards Grand Junction, it goes all over the place. And that's because the water is diverted into the valley for agriculture, and the toxin would then spread all over the place. And there's a look at the Grand Valley towards Grand Junction where the water would flow. So let's go back upstream again towards Lake Dillon. What we want to do is we want to find out how much water flows into Lake Dillon, or how many kilometers of streams flow into Lake Dillon. So let me just do a few things here. I'm just going to clear my navigation there. I'm going to clear that green dot, and I'm going to change my navigation to something called a selected feature. And we're actually going to measure in real time then how many miles or how many kilometers of streams flow into Lake Dillon. So I'm going to zoom in and put another green dot on Lake Dillon. There it is. And let me just go back to the previous display. And then I'm going to navigate upstream. So I'm going to go up here to this box and say trace upstream. And there's a solution. So there's all the streams that flow upstream from Lake Dillon. And notice there's a patch of streams right in here that aren't part of the network. And the reason for that is,
we got a question.
Oh yeah, go ahead for the question, yeah.
Yeah, it's asking if the model can show the dilution as the spill flows downstream.
Well, you can do that because you know how many cubic feet per second are flowing through the streams. And so it would be possible to create a model to do that because you know basically how much water is flowing through. And I said that it's on an annual basis, but you can also do it on a monthly basis too. So if you wanted to know, for example, what the dilution would be in September, you could do that and get a better understanding as to how much the toxin will dilute through the water, not just through the length of the water, but the flow volume of the water. So the answer is yes, you can do that. Now, I don't have that set up on my computer, but there are scientists, particularly at the Environmental Protection Agency, that do things like that. And they use this data, they use this model to do things just like that. So I was talking about this area here that doesn't have any flow in it. That's because these streams are not connected to the Blue River. The reason for that is that they flow through the gravel. And so the streams kind of disappear in the gravel, and then they eventually flow into the blue, but not directly. So for the purpose of mapping, we don't have them connected, but you could connect them if you wanted to. Let's just take a look then at how many kilometers of streams we have flowing through the lake here. So what I'm going to do is just a few kind of GIS things. GIS stands for a Geographic Information System. And that's a computer software that allows you to figure out things on a map. So for example, on your cell phone, when you want to figure out how to get from one place to another, there's actually a geographic information system on your cell phone that allows you to figure that out. Most people call that a GPS, or a global positioning satellite. So just lay people call it a GPS, but technically it's really called a GIS, which is the software that I'm using right here. So I'm going to look at this attribute table. For this data here. And for all the segments that are flowing upstream, I have a length in kilometers for each individual segment. And what I'm doing right now is I'm just going to add those up. So I hit this thing here called statistics, and it tells me that there are 1,466 kilometers of streams flowing into Lake Dillon. So you ask, why not miles? Well, scientists always measure things in kilometers, and so this database is set up in kilometers. So 1,466 kilometers is roughly about 1,000 miles. So there's roughly about 1,000 miles of streams that flow into Lake Dillon. Now, a big part of that is ephemeral streams that don't have water in them all the time. So say we wanted to eliminate those streams out of our calculation and just deal with perennial intermittent streams. So I'm going to go here and click on this thing called selection and select by attributes. And I'm going to look at the flows, and I'm going to remove from the current selection all of the streams that are ephemeral. So I'm going to go to something here called the F code. And if you're a scientist, this is all makes sense to you, but it'll make sense in the end. I'm going to eliminate the ephemeral streams. And if you watch the map display here, magically the ephemeral streams will disappear. So watch this. There, the ephemeral streams just disappeared. And you can see these by these small little segments here. Now we're going to remeasure how many kilometers of stream are upstream of Lake Dillon, and figure out what it is without the ephemeral streams. So I'm going to go to the flow line here. I'm going to open up the attribute database. I'm going to look at the length in kilometers of all those streams. And I'm going to get an answer of 1,033 kilometers. So it's still not, doesn't eliminate that much. So roughly, there are about 700 miles of streams that flow into Lake Dillon. That's an awful lot, probably a lot more than you would have guessed. But that's how big the network is. And just to give you an idea, there are 7.5 million miles of streams in the United States. And this is an example of some of those streams. So that's what I have to present today. I can take any additional questions if you have any, but that's basically the presentation.
Awesome. Thank you, Jeff, for doing that. We'll give it a minute to see if anyone else has any questions about that. Yeah, just a huge thanks to you, man. I really appreciate you reaching out. This is very interesting knowledge, and it's quite apparent that you've dedicated a large portion of your life to learning about these systems, and it's pretty impressive, your knowledge. Do you want to, so you've written a book about this stuff too. Do you want to chat about that with the people at all?
It just so happens that I have a copy of my book with me here. This is on Amazon. If you go to Amazon and type in my last name, Simley, S-I-M-L-E-Y, you can find the book. And it tells all about what I've just talked about today. What I've shown you today is for the Dillon Ranger District, but we can do the same thing for anywhere in the United States. And there are thousands of scientists out there who use this data to analyze things. One person asked about if there's a toxin in the water, how would it dilute? There are scientists out there that do that. There are people that analyze the fish habitat, where fish can migrate and where they're unable to reach spawning grounds. The Forest Service is a big player in all this data. They help build this data set. In fact, besides the U.S. Geological Survey, the Forest Service was one of the major contributors of money to this program. And they use this data for analyzing lots of things. A big thing is fish habitat. Another big thing is if there's a forest fire, they're concerned about what happens to the debris that flow into the rivers after the fire. And so that's one of the reasons why they funded this project and made this all possible. But the book talks about all this and lots of other things. So if this is of interest to you, the book is $33 on Amazon, and it's 800 pages, and it's a great book.
Awesome. And I just, in the comment section, wrote down your name so they can look it up.
Yeah.
Go. But yeah, huge thanks to everyone for tuning in. As I said, this is very unique information that we're getting from Jeff, and you know, I'm pretty fortunate that he reached out to us and that we're able to go over this presentation here. But yeah, huge thanks for tuning in. This will be available both on our Facebook page as well as on YouTube in the near future. So you can spread the word and let other people tune into it. Our next webinar series, we're going to take a couple weeks off here. Our next webinar is on the 9th of July, and it's the second part of Joe Newhart's geologic history of Summit County, and he's going from the end of the Paleozoic to the formation of the Rockies. We've also just kicked off our educational hike series this week. The second one of that is on Saturday. We're going to look at the edible plants in Summit County. There's still 2 spots open, so if you're interested in that, sign up online. We'll have to be a little strict with the COVID protocols, but we're making it happen. But yeah, huge thanks to Jeff and huge thanks to everyone for tuning in. And check one more time. There's no more questions. Yeah, we're all set. So I'll sign us off here, Jeff. Thanks,
okay,
guys.
thanks.
All right, we're off live. Thank you. Thanks so much for doing that, Jeff. It was pretty well attended. We had 13 people tuned in for most of the time, which is more people than we have for any of our hikes. And as I said, this is posted and we're getting over 200 views on all of them within a week that I've checked. So it's going to get great reach, and this is awesome knowledge. So thanks so much for volunteering to do this, man.
Yeah, and when you have this up on YouTube, shoot me an email. Let me know how to link to it.
Absolutely.
And I know a lot of people that'd like to see this. So
sweet. And I can I'll put an Amazon link in there too to your book as well if you'd like.
Okay.
Yeah, I think that would be nice, and hopefully bolster a couple sales. And I can put that link in the Facebook comment thread as well. But I'll get this up here the next day or two.